Hello, everyone. It's our third colloquium in this semester. So welcome to our electrochemical colloquium today. Today we're discussing electrochemistry of single particles and single redox events. So our speaker is Professor Henry White, who is one of the pioneers in the field of nanoscale electrochemistry and is also well known in the field of physical materials chemistry. He received his PhD from the University of Texas in Austin in 1983 under the guidance of Alan Bard. And then after his postdoc at MIT, he became a professor at the University of Minnesota. And since 1993, he is a distinguished professor at the University of Utah. So Henry, thank you so much for joining us today. Please feel free to start at any point. The stage now is yours.
Thank you. Let me see if I can share my screen. Okay. Well, Andrew, I really appreciate the invitation. The colloquium has just been a tremendous success. So it's a real pleasure and actually an honor to participate in this. And
we're really happy to have you here. Yeah.
And let me say good morning. Actually, I probably should say good afternoon or good evening to a lot of people. It's very early in Salt Lake City, but this is worthwhile getting up for. So thanks again. Okay, so as Andrew said, the talk today is sort of my perspective on the field of electrochemistry in measuring single particles and single redox events. And by particles, I use the word particles in a very broad sense. This could be anything from atoms or molecules. They could be really particles. They could be biological entities, small particles like DNA, or they could be vesicles and even maybe electrons. And so what I'm going to do, I split the talk into two parts. The first part is an overview of some of the key concepts and the motivation for electrochemists developing techniques to measure single particles and to look at single redox events. And I'm going to go through some of the principles. When you're working with single molecules, unlike when you're doing experiments with large ensembles of molecules, you tend to work or do the analysis of using statistics because these processes are going to be stochastic. So it's very different than using differential equations, for instance, for modeling or interpreting voltammetry, cyclovoltammetry. And then I'm going to go over, there's one general strategy that applies to all of these measurements, how you set up the experiment to detect single events or single particles. And I'm going to go over that. And then most importantly, I think, is do we learn anything useful about chemistry and physics and electron transfer reactions by making these measurements on single particles? And then I'll talk, the first half of the talk, I'll finish up by discussing what the limit of detection is, what you can measure and what you can't measure. Okay, so it's a little bit of design rules if you're thinking about making measurements on single molecules or single particles. And then after the break, I'm going to give, I've got 3 short stories from my laboratory. This is all unpublished work. And we'll see how far we get through with this. There's 5 or 6 slides on each of these topics. But I'll talk a little bit about recent work on looking at carrier transport of ions through bilayer films, in particular valinomycin, and our work to detect single molecules transporting ions through a bilayer and how much current can a single molecule carry. And then I'm going to tell you about something that's unfinished work is a project where we're trying to measure a single electron transfer event. This is something that hasn't ever been done before, and we're not quite there, but we have ideas on how to do this. And then the last topic concerns nucleation of metals and using techniques, nanoelectrode techniques, to actually count the number of atoms that comprise the critical nucleus necessary to grow a particle. So that's the outline for the talk. The motivation for doing single particle or single event electrochemistry, there's really two things here. Electrochemists are interested in measuring the behavior, fundamental behavior that can't be observed when you're doing measurements on large numbers of molecules, ensembles of molecules. So that's one motivation. That's sort of the fundamental motivator. The other motivation is to develop ultra-sensitive electroanalytical methods for measuring, for instance, how much DNA is in the solution or how many particles you have in the solution. So again, here's the definition of particle I'm using. Particles, atoms, molecules, soft, hard, nanoparticles, biomolecules, vesicles, electrons. I put a question mark by electrons because that story is not complete. Okay, so if you look at the literature, starting in about 1995, it was just an explosion of research started on single particle and single redox event electrochemistry. And this is just a short list. I just ran out of space at the bottom of the slide. I was writing this up, but people now can routinely detect single molecules. There's papers on monitoring the motion, random motion, diffuse Brownian motion of individual particles near an electrode surface, counting the number of neurotransmitter molecules released during exocytosis, measuring the activity of a single electroactive enzyme. I've got a question mark there because I'm not sure that's going to stand up to the test of time. A lot of work on looking at reactivity structure relationships of electrocatalytic particles, one at a time, looking at the electrochemistry on a single particle, and then looking at the structure using electron microscopy and then correlating the activity to the structure. Particle size characterization and measuring the concentration of particles in the solution. This is pretty routine now. Counting atoms and molecules and phase transition nuclei. I'm going to touch on that today, hopefully. Al Bard's group has done quite a bit of work on electrocatalysis, such as hydrogen evolution at single platinum atoms or clusters of platinum. And then a lot of spectral electrochemistry, optical and Raman detection of single molecules or single redox events. So the list, this is just a partial list. There was a really nice review paper that appeared 3 days ago by a good friend of mine who stated that nanoelectrochemistry and nanoscience of electrochemistry, single particle electrochemistry was a niche area of electrochemistry. And I really think that's, I disagree with that completely. This field has exploded and it's mainstream electrochemistry now. There's no going back. People still do conventional measurements, but the nanoscale electrochemistry and single particle, single event electrochemistry is a major part of electrochemistry now and here to stay. So what happened? After in 1995, we saw this explosion, and I think the reason for that, at least partly the reason, is that shortly before that we had the development of STM in the early 1980s. This is an STM image of halogen atoms sitting on a silver 111 electrode from my lab. This is the ultimate single particle electrochemistry experiment because you can see single atoms and you can see single molecules. You can do this all in situ. And very shortly after STM was invented, by 1990, not every electrochemist, but a very significant fraction of the labs, electrochemical labs, had an STM, because this is the way you could really see surfaces under or in an electrolyte phase. And then 10 years later, the first single molecule spectroscopy experiments appeared. All right, and so this is an image of molecules sitting on a surface. They're fluorescing under illumination, and you can count the molecules and you can take the spectrum of these molecules. So these two things predated single particle, single event electrochemistry by a few years. And I think, electrochemists certainly were paying attention to STM and sort of getting this idea that we should be looking at single atoms and single molecules. And some electrochemists, I think, were looking at the single molecule spectroscopy as well. So what I want to do is now, if I can get my slide to move, is just give you a couple of examples of the very first, these are very early on, 1995, of the first reports of single molecule electrochemistry or single reaction electrochemistry. So the first single molecule paper was from Bart and Fan, published in Science, where they took a scanning electrochemical microscopy tip, a metal tip, very sharp tip, with a diameter of about 15 nanometers, and brought it up to a surface within 10 nanometers and trapped a molecule, single molecule ferrocene. I'm sorry, my slides are jumping. And then you can oxidize the molecule at the tip, and then it diffuses to the substrate where it's reduced, and you cycle this over and over 1 million or 10 million times per second, and you generate enough charge to actually measure the electrochemical current. So that was the first single molecule report, and it was quite controversial at the time. It's been repeated now in 3 different labs with using different types of systems to trap a molecule. So it stood the test of time, but that got people thinking about, what can you do if single molecule electrochemistry? Well, I'll talk more about that later. The same year, Mary Ann Collison and Mark Whiteman published a paper in Science where they were looking at electrochemical generated chemiluminescence. And the experiment is to take a small microelectrode, a gold wire, and reduce diphenylanthracene to make the radical anion. And then you switch the potential quickly and you oxidize some DPA to make the radical cation, all at the electrode surface. And then the anion and the cation annihilate each other to make a ground state DPA and an excited state molecule. The excited state immediately, within a microsecond, returns to the ground state and emits a photon. That's the luminescence. And they showed that if you set this experiment up correctly, and you use fast time monitoring of the photons hitting a photomultiplier tube, they could see individual photons arriving, corresponding directly to this reaction. But what they were interested in is looking at the kinetics of this reaction up here. And so by using data like this, they were able to back out a rate constant for this reaction. And not surprisingly, it was diffusion control. So I think that's the first example of a single reaction being monitored. And then about 10 years later, another hallmark paper came from Bernadette Quinn and Serge Lemay on looking at the collision and absorption of polystyrene particles on a small microelectrode. And the experiment is set up by, you have molecule in the solution, something like ferrocene again, and it's being oxidized at diffusion limited rate. And then one of these insulating particles absorbs on the surface, and it partially blocks the flux of the molecule to the surface, and you see a decrease in the current. Here's experimental data over here. And I believe this is the first example of what's called now a collision or impact electrochemical experiment. And it just really woke up the community. There's many different variations of this experiment, and there's probably hundreds, if not thousands, of papers published a year doing collision or impact electrochemical measurements to detect particles and to characterize them. Okay, so here's some of the principles. I thought we should talk a little bit about this. what's the difference between classical electrochemistry? So that's like cyclic voltammetry based on Nicholson and Shane, or square wave voltammetry, Oster-Young square wave voltammetry, where you're dealing with a large ensemble of particles and molecules. So we're talking about concentrations, typically 10 to the 18th to 10 to the 22 molecules per liter. You do these measurements, the analysis is based on the concentration of the redox species. You typically use macroscopic electrodes, millimeter dimensions. The current potential or current time response are based on deterministic expressions like Fick's laws or kinetic expressions, differential equations. And then the simulations that you use for when these reactions get complex are typically finite difference and finite element simulations to approximate the differential equations, these expressions up here, okay? In contrast, when you get down to single particle, and this should be single event electrochemistry, instead of working with concentrations, the analysis is based on the number of particles. And frequently the electrode or active area is nanoscale to microscale as opposed to millimeter. And the current time, current potential responses are based on stochastic analyses. Frequently, these processes are governed by Poisson descriptions. And then instead of using finite element or finite difference simulations to model what's going on, frequently Brownian lattice type simulations are used. This is really coin flipping, for instance, to watch a molecule diffusing around or to simulate a molecule diffusing in solution or to simulate if an electron is being transferred at the electrode surface. So there's differences in the types of analysis. This is the world of differential equations at the top. And this is the world of Poisson in the bottom, all right? And I would suggest this is actually simpler. Using coin flipping is much simpler to do the analysis than doing differential equations. Okay, let me just give an example of deterministic versus stochastic processes. This is, I just made this example up. This is a thought experiment. This is the old Chris Chidsey experiment, where you have a gold electrode and you have a self-assembled monolayer of alkyl thiols. And some of the thiols have an electroactive center. This could be a ferrocene center. And the experiment is to apply a potential so that you drive the oxidation of ferrocene to ferrocenium. So electrons are moving from the redox group tethered at the end of the SAM layer, and they're transferred or they tunnel to the gold electrode. And the experiments, when Chris did these experiments, and other people have done them too, the surface coverage of ferrocene is on the order of 10 to the 12th molecules per square centimeter. They used a macroscopic electrode, 1/10 of a square centimeter. So the number of electroactive molecules on the surface is about 10 to the 11th. That's a huge number of molecules. So when you do this potential step experiment, the current decays exponentially. This is a first order process. The concentration of ferrocene that hasn't reacted decays exponentially. And here are the results of the kinetic equations here. So this is very classical. You know, I'm using differential kinetic model, the differential equations from kinetic models to get these equations. You're not worrying about individual molecules here, and you can predict the response before you do the experiment. You may not know the rate constant, but you know this is going to be an exponential decay, all right? Now let's do the same experiment. All we're going to do is change what I've highlighted in yellow here. Instead of using a macroscopic electrode, we're going to use a 10 nanometer radius disk. And now the area is 11 orders of magnitude smaller. This is doable. This is easy to make a 10 nanometer disk. So this experiment is something you could go in the lab and really do this. And then now if you multiply the surface coverage by the area, it turns out there's only 3 molecules, 3 ferrocene molecules sitting on the surface. And now the question, what's the response function over here when I apply the potential step to drive the electron transfer, all right? And so I put a question mark up there, and This is something I actually use in teaching. I always pause and let students think about this. I can't pause too long here because I got too many slides. But this is what happens. This brown line is corresponds to the surface coverage of the ferrocene. You only have 3 molecules, so you apply the potential, and it's a first order process. It's completely stochastic. At some time, an electron transfers, so you only have 2 ferrocene molecules. At a later time, the next one transfers, you got 1, and then the third one transfers, okay? And if you set the experiment up and you did it again, you get a totally different response because it's purely random, all right? So the first electron would transfer at a later time, and so on. So this is pretty easy to understand. Now, if you went and did the experiment, what I've shown you here is exactly how the system would behave. You would see step decreases in the concentration, but now you ask, well, what would the current response look like? And the answer is when the electron transfers, there should be a little current spike here. Should be a little current spike here. But of course, if you think about this, you can't measure that because you're talking about measuring the charge of a single electron, and that can't be done, or it hasn't been done in electrochemistry. Yeah, it's been done in physics at very low temperature, but not at electrode-electrolyte interfaces at room temperature. Here's another example. This is from my lab. This is a real example looking at the oxidation of ferrocene to ferrocenium in a pseudonitrile solution using a 10 nanometer radius electrode. And here's the voltammetric response. You scan out and you start oxidizing ferrocene, and it becomes diffusion limited. And it's a small current. This is about 50 picoamps, the limiting current here. And you say, well, what does that correspond to in terms of the number of molecules being oxidized per second? And it's on the order of 10 to the 8th molecules, ferrocene molecules being oxidized per second. And you say, wow, that's a really small electrode. That's still a lot of molecules. How do I get down to single molecule events in this experiment? And you can think about strategies. There's different strategies. You can reduce the concentration of redox species from, this is a 5 millimolar ferrocene solution. You could go to nanomolar. And that reduces this event rate by a factor of 1,000,000. And then you could decrease the time scale of the measurement. This is a very slow voltammogram. You could go from seconds to milliseconds. You easily get down to a molecule per second, arriving at the electrode surface. And so now you're into single molecule regime, but you still have the same problem because you can't measure a single electron. So it begs the question, how many electrons do you need to detect a particle or an event? And I'll address that later on this morning. All right, here's the general strategy for all single particle, single redox event measurements. I underline, if you're in the courtroom, if you're a witness, you're told never to say never, or never say always, never say all, never say none. I've used the word all because I think this is true for everything that's been reported in the literature. And if someone has an example where what I'm going to tell you is not true, I'd like to hear about it. But the general strategy is to confine the particle or the event either in space or in time. So get down to a few particles or a few molecules by constraining the space you're working in, or by doing fast measurements. And then you have to couple that to some type of amplification. It could be a chemical or physical amplification, but because you can't see single electrons, there has to be an amplification. And it turns out the amplification that's usually required is always about 10 to the 4th, 10,000 or greater to do these measurements. Okay, so let's take that rule that you have to have confinement and amplification. Go back and look at these early experiments. The Frank Fenn and Bard experiment, well, the confinement part is bringing the tip down and isolating a single molecule. So there's only going to be one molecule There could be two or there could be zero, but typically it's one molecule. They set this up so it's one molecule. And then the amplification results from the fast diffusion between the tip and the surface. And you get on this, 1 million cycles per second, and that generates enough charge that you can measure a recorded current. All right. The Collison and Whiteman experiment, okay, well, this is a microelectrode in bulk solution. So it doesn't really, at first glance, it's not obvious what the confinement is, but the confinement is that the molecules, the reactive molecules, are constrained close to the surface in the diffusion layer. All right, so if this is a 2-micron electrode, all these molecules being generated are within 10 microns of the surface. That's a volume of about 10 to the minus 12 cubic centimeters. They still got a lot of molecules there. There's 100,000 molecules in this experiment in the diffusion layer. All right, that's too many to do make observations of single events. All right, so the way they take the 100,000 and get down to one event is by resolving it in time. All right, so this is the ECL signal, the fluorescence signal, at on time scale of hundreds of seconds. It's a continuous signal measured at the photomultiplier tube, and then you crank up the resolution by 1 million, and you can see the little blips. And they wrote in this paper, it's the same thing that I'm telling you, is that we show that single reaction events can be observed by restricting the volume occupied by the reactants and the observation time. All right. Okay, so that's the confinement part of this. And then the amplification is trivial here. It's a photomultiplier tube with a gain of greater than 1 million. All right, let's see. And then going back to the Quinn and LeMay experiment, the particle absorbs on the surface. So the confinement is you're putting a particle right at the sweet spot where the flux of the reactant molecule is highest. All right. And the amplification is you're blocking the flux of the redox molecule. So these steps here, if you take the current, these steps correspond to blocking the flux of the redox molecule, corresponding to a flux of roughly 40 million molecules per second. All right, so the amplification here is on the order of 40 million. Each particle blocks the flux of 40 million molecules. All right, this is true in all of single molecule, single particle, single reaction redox electrochemistry. Okay, now I put this slide in. What do we learn? Do we learn anything fundamentally new here? Because there's sometimes you hear criticism about people doing really cool experiments where there's not a lot learned. And so, I thought about this. If the experiment is successful, if you construct a new experiment to measure something, and it's experiment, it worked the way you kind of thought it was going to work, there's really two outcomes. One is that you learn a new method of measuring something that you're already understood, and you could have measured it by other conventional means. And I would say, I don't know, 80% of the single molecule, single particle experiments fall in this category. Number one, really fantastic, difficult, sophisticated, cool experiments, but you're not getting out a lot of new information. The other outcome is that you measure something that nobody else has previously measured, and you learn something, new behavior, fundamental understanding of electron transfer reactions. And that happens, more and more, the results are coming down into the second category. The first 5 or 10 years, it was really developing methodology that didn't exist anywhere. So we go back to this Fan and Bart experiment, and you say, what new fundamental information was obtained here? Okay, well, we learned a molecule diffuses between 2 electrodes. And in fact, back in the late 50s, Thin layer electrochemistry was developed, which involves redox cycling between the two electrodes. And the equations developed in the late 50s are used to actually analyze this experiment right here. So you kind of see, well, there's not a lot fundamental, really new stuff that's being involved, but it is a fantastic method. And if you look at the literature after 1995 and you track where this experiment went, well, it went from one laboratory to another, people developing it, reproducing this experiment, doing new things with it. And a recent example of something that's very similar is work from Syl Box and Paul Bone at Notre Dame, where they build a little nanopore with two closely spaced electrodes and trap a single molecule and do this redox cycling, just like this, to get very large currents. And it's much more sophisticated. They have a membrane here that allows selective transport of the analyte into this little well. And it's not just one little nanopore, they may have thousands of these on a silicon chip, all in parallel. So they get huge signals. And this has turned out to be a quite interesting and potentially useful analytical device, because you can measure very low concentrations of species and get very high electrochemical signals. All right. So the point here is that if you look at this could be criticized, this early experiment. Well, you didn't learn much, but it set the stage for 25 years of work to get to devices like this. All right, so this experiment got amplified by a factor of 1,000 over 25 years. If you look at the Collison Whiteman experiment, where they're counting photons for this reaction up here, this is 1995. Well, by 1975, this was completely understood. The rate constants were measured. And you could claim you didn't learn anything from this. But this experiment grabbed a lot of attention from the community, coupling light, doing single molecule spectroscopy at electrode surfaces to get out information. This is an example recently from Bo Zhang's lab at the University of Washington, where they have a transparent electrode and they shine light up through it, and they excite molecules that are absorbed on the surface as a function of the electrode potential. And the molecule they're using here, if you reduce this guy, it goes from a non-fluorescing or weakly fluorescing molecule to one that's highly fluorescent. And so these 9 images here show the image of the electrode. All these little bright points are single molecules, and you're scanning the potential starting at the left. You're going negative, all right, or it may have this backwards. You're cycling, they're doing cyclic voltammetry, and they're watching this reaction occur, or this one, I'm not sure which one, and they can see the molecules turning on and off, the luminescence, the fluorescence from them. And this is a really important experiment. There's lots of reports of doing this. It's important because you can look at the heterogeneity of the electron transfer activity on the surface. So you can correlate, if a molecule's sitting at a step, it may have a different, the energetics of electron transfer may be different, and you can monitor that by looking at photon emission. And then this nanoparticle collision experiment, polystyrene adsorbing on a microelectrode in JAX. I was the associate editor who handled this article, and it almost didn't get published because I was being kind of dull at the time. I wasn't thinking clearly, and I just thought, polystyrene adsorbing on a surface, and you see the current go down, that doesn't seem very interesting. And boy, was I wrong. This nanoparticle collision in the United States and in Europe, everywhere, in Asia, it's just been remarkable how this area has exploded. And just to show you how the technique's been refined. Instead of polystyrene particles hitting the surface and blocking the flux, you can do this if you reduce the size of the electrode from microns to 100 nanometers. Then you can start seeing things like DNA absorbing on the surface and blocking the flux of molecules. So every one of these little steps, this is from Jeffrey Dick and Al Bard, these steps correspond to the absorption of one molecule of DNA in solution. And if you measure the frequency of absorption here, you can back out the concentration of DNA in the solution. I'm not showing you the equations. Okay, so let me change gears a little bit here and talk about the limit of detection. And this will be the last topic before the break here. And the question is, in these experiments, how many electrons do you need to measure something? All right, and I put a statement up that's obvious to anybody who's done any electrical measurements. One electron cannot be measured. It's well below the detection limit of any electrochemical method based on measuring current. Okay, so mathematically we can say the minimum number of electrons is greater than one electron to do these single particle and single redox event measurements. All right, and then the question is kind of begs the question, what is the minimum? All right, and you can go to the literature and look at what people have measured. And these are two examples from England, from Pat Unwin's lab and Richard Compton's lab. These are two laboratories who do really state-of-the-art measurements in this area. And the top one here, this is an SECCM measurement. They're scanning a probe over a surface and looking at redox activity, if I remember correctly. And these little blips are an increase in the activity when they scan across a step edge. All right, I hope I'm recalling this correctly. And so if you take this guy right here, this little guy, this is the smallest peak here. And if you know the scan rate, how fast they're scanning the tip, you can integrate this and get the charge under this little peak. And it corresponds to about 1,000 electrons. And then in the Compton experiment, this is a single particle collision experiment. And this is a silver particle, small silver particle colliding with an electrode surface. And when the particle collides, the potential of the electrode sets, so it oxidizes the particle, and you get this nice blip. So that's one particle colliding with the surface, and the area under this corresponds to 50,000 electrons. And clearly, the signal to noise here is fantastic. They could have detected a much smaller peak corresponding to 10,000 electrons. So we can be a little bit more precise here. The number of electrons, the minimum number of electrons you need, it's greater than one. And apparently it's less than or close to 10,000. All right, this is the experimental measurement. And if you look at, there's a lot of literature, there's just tons of literature on these single particle, single event measurements. And the very best ones always kind of come out around 10,000 electrons. It depends on the frequency that you're doing the measurement at, but you know, on these time scales that are relatively slow, you know, 10,000, you need at least 10,000 electrons has been measured. We know one electron can't be measured. So what's the number? What's the magic number in between? All right. And to cut to the chase on this, because I don't want to spend too much time on this, the limitation here is the so-called shot noise limit. And it's due to the fact that you're counting electrons, and electrons are quantized. They have a 1.6 times 10 to the minus 19 coulombs. And the discrete charge on each electron introduces a statistical limitation on how small of a current you can measure. All right. So I've got two examples here to illustrate this. This is this microelectrode experiment where the limiting current corresponded to 10 to the 8th electrons per second. So in a 1 millisecond experiment, this is 1 millisecond, I'm going to count 10 to the 5th electrons. And there's so many electrons. If I'm counting electrons, the number of electrons remains pretty constant because there's so many. Occasionally there's that blip. You're counting 2 electrons at this point. Occasionally there's no electron here. But if I take a delta T, this time period here, and I count up all the electrons and divide by delta T, which gives me the current, it's going to be the same here as it is here, as it is here, but just because you have so many electrons. But now if you do this experiment from Pat Unwin's lab, where you're looking at really small currents here, this is down in tens or hundreds of femtoamps, and you got 1,000 or 10,000 electrons in this experiment. And let's say this is, I forgot what the time scale is. Let's say this took a second to scan over this little peak here. Now let's blow this up to 1 millisecond, because that's probably the collection rate that they were taking the data. In 1 millisecond, you only have 10 electrons. And the shot noise limit, what the deal here is that they don't arrive at a constant rate. All right, so early on in the experiment, you might have 3 electrons being counted in this delta T. This one you have none, and then over here you have 6 or 7. All right, so the current's going to change, and this is what I'm showing here. This is the dashed line is the average current. This is what you measure. It's the average current over these 3 time increments, and you see it doesn't change. But down here, when you're counting a very small number of electrons, the average current changes dramatically. It's 0 here, it's high here, and it's kind of low here. And this variation in the current over these time increments gives rise to shot noise. All right, and we worked this out. My colleague, Joel Harris here at Utah, taught me how to do this and worked with us. And I'm not going to go into the theory or the math in any detail. I'm going to give you the final equation here. This is what we call the limit of quantification, not the limit of detection, but the limit, how many electrons do you really need to measure something and quantify it, all right? And so that's what this is. This is the minimum current you need to do analysis in electrochemistry. It turns out to be 21,000 times the charge of an electron divided by the delta T, the time of the measurement. It's a very simple expression. We're very fortunate. Richard Compton let us publish this in Current Opinions in Electrochemistry. And it's a nice little neat equation. Does it work? Well, what we did is we went to the literature, 25 different laboratories. These are the names of people associated with these laboratories. You'll recognize a lot of these people. These are people who are well known for low current, low noise measurements. And then up here, here's another 6 examples where we show what the experiment is. And we looked at all these experiments. So we measured, this is an experiment from Serge Lemai's lab where he's got a single molecule cycling between 2 electrodes. So this is the old Bard experiment, but done much better now. Well, I shouldn't say that. Bard will kill me if he hears this. And when a molecule enters, you get a increase in the current. So you can measure the delta I, how much the current has changed, and you can measure the time, and you plot up these points. I think this point right here corresponds to this experiment. This is delta I. This is the signal that was measured from these 25 different labs around the world. And this is 1 over the observation time, delta T. And so all the points and symbols, these are all experimental values. I think there's 70 some different experiments from 25 labs. And the brown dashed line is this shot noise limit. This is the theoretical prediction. And you see, lo and behold, seems to work. There's all the experimental evidence from the best labs in the world are above this line. And the theory says, if you're down here, your experiment's not going to work. You're not going to be able to measure anything. And we were unable to find any experiment, published experiment, that falls below this brown line. There's two lines here. There's a black line. This is the shot noise limit if your baseline is absolutely zero. And this is the shot noise limit when you have a baseline current, and it's larger. The brown line is displaced. And that's because the background or the baseline current also has shot noise in it too. The baseline current is a really small current too. And if you look at all these experiments, they all have significant baseline currents. So in the Unwin experiment, the baseline current is about 5 picoamps, and you're looking at 100 femtoamp peaks here. The LeMay experiment, the background current baseline is 10 femtoamps, and you're looking at a change of about 2 femtoamps. So you have to take into account the baseline current as well. So this plot is useful. I mean, it seems to work, even if you disagree at how he came about deriving the brown line. All right, it's a good predictor of what can be done and what can't be done. And we're going to take a break now. And after the break, I'm going to show you how we use this equation in recent experiments to predict whether or not the experiment's going to work. So I'm going to take a 5-minute break here, and I think I turn this over to Andrew.
Thank you so much, Henry. We are open to questions. Please feel free to ask questions. You can ask them in the chat or directly.
Let me see. Let me open chat.
Yeah, in the chat, one question is 21,000 for.
It's 2,100. Did I have it wrong on the slide?
No, I think it was correct.
Did I say it wrong? This is correct. The question was, is it 21,000 or 2,100? The number is 2,100.
Okay, maybe I can start. One question that I would still like to maybe a bit more clarified is regarding the fundamental information. So of course, from what I understand, in these experiments, you can detect the events, but that's the detection of the event is the type of information that you get. So you don't get any inner structure of the event itself, how it was, yeah. And so one question is that, what are the fundamental quantities that you, in principle, you can get? So of course, something about the diffusion and the collision processes, but maybe you can list sort of the major fundamental quantities that we can get from these experiments, going sort of beyond the detection and the statistical analysis.
Correct. Yeah, and I really haven't shown that here. I will in this after the break. I'll show examples of fundamental information you can get. But you can get, this experiment up here by Richard Compton. He's done a lot of this electrolysis, collision, or impact electrochemistry. And, you can measure, in this particular case, the peak height, the charge tells you about the dispersity of the particles in the solution. That's sort of an application, okay? Maybe not so much fundamental, but a really important analytical measurement. The BART experiment over here, these are voltammograms recorded at either a single platinum atom. This is sitting on a bismuth surface, and you're looking at hydrogen evolution. And so this is platinum 1, platinum 2, up to platinum 9. And you can see these waves are shifting. The larger the cluster of the particle, the less overpotential you need to reduce protons. And so what was learned in that experiment, and get back to it, sorry, is that there is a dramatic increase in the rate constant for hydrogen evolution as you go from platinum 1 up to platinum 9. There's a 1,000-fold increase in the heterogeneous rate constant going from 1 atom up to 9 or 20. And so there's lots of things here, and and the Unwin experiment down here, they're mapping out the activity as a function of the structure of the electrode. over here in the LeMay experiment, there's diffusion, there's redox cycling, but there's also evidence that by measuring the current and working through the analysis, that the molecule is not just redox cycling, but it's adsorbing for a very short time at the electrode surface. And when it adsorbs, when it's adsorbed, it's not diffusing, so the current decreases. All right, and then on particle collision experiments, there's a lot of particle collision experiments. I didn't talk about them because I just don't have time. Instead of doing this experiment where you're looking at insulating particles, this could be a catalytic particle that comes down to the surface. And it's when it hits the surface, there's a increase in the, or burst of current or step increase in the current from the catalytic reaction that's being carried out. So you can start measuring, looking at rates of reactions as a function of the size and the shape of the particle. Effects of the shape of the particle. There's a very nice paper by Lane Baker in the last year or two looking at how catalytic activity, I've forgotten what the reaction is. I think it's either oxygen evolution or hydrogen evolution, how that activity changes with the shape of the particle. And they did the measurement, one particle at a time, and then you go look at the particle, you get the exact shape, and you can say, oh, this structural feature is important for the catalytic activity.
So they could look at the particles before they hit the electrode.
No, it's the particles on. They're putting one particle. The particles are on the surface, and I believe they're using scanning electrochemical cell microscopy.
Oh, in that case, yeah.
To interrogate the electrochemistry one particle at a time.
Okay, one question is about the data that you showed on one of the last slides, where you have the equation and you say that there's a fundamental line. So do you have so the data for the ion channels in biological cells, how does it correlate sort of with this plot? Did you consider the data?
Yeah, I mean, oh yeah. So the ion channel, let's look at the nanopore current time recordings. So the black dots here are mainly biological ion channels. So like alpha hemolysin. Okay, and you're looking at discrete events. You're in this case up here, this is from my lab, this is alpha hemolysin. We got one molecule of DNA here in the alpha hemolysin. And we're applying a potential. This is inserted in a lipid bilayer. We're applying a potential across this, measuring the current. And right here where the arrow is, all right, this chemistry is going on. These are going from here to here. I'll start over here. You're flipping out. This is a mismatch, two cytosines, and a cytosine flips out. All right, you break a hydrogen bond, and when you do that, the current goes up, and then when it goes the other direction, the current goes down. So that's a single reaction event, and you see that this noisy looking current time trace. Each one of these little pulses is this reaction going back and forth, back and forth, back and forth. Okay, and so that's this is not fair date chemistry, but it's an electrochemical measurement, and so the numbers from these types of measurements, the biological measurements, they're right on the plot with the more conventional electrochemical measurements.
So they're pretty much in line with the conclusions. Okay, I hope that it was one of the questions from the chat. So. Another thing is, let me see, the impurity in the electrolytes. Do you see that being a problem? Like the electrons have to be super pure because when you detect single events, of course, you can get impurity issues.
Oh, sure.
Or because you make the electrodes so small that it doesn't really play any big role in detecting single molecules and single events.
Well, you can make the electrodes so small that you don't see anything. A particle rarely, the arrival time of a particle to a 10, say a 10 nanometer size electrode, you may only get 1 per hour. And that's a poorly designed experiment. So you would use a 10 micron size electrode, and then the frequency of arrival is higher, and you can see a train of pulses like you see here from the in this experiment from Richard's lab. Okay, impurities, it's the same. I think the impurity question is similar for these types of measurements as it is for conventional measurements. The impurity question is sort of a lab to lab question and experiment to experiment. Some of these, platinum, this experiment, the platinum clusters, I always found this surprising. I mean, it works. I find this surprising, but they're doing this in water. This is a perchloric acid solution, and you got impurities. You got some trace organics. You got trace other stuff, and diffusion to diffusional transport of impurities to these small particles is, occurs in less than a microsecond. And it's always shocking that you can keep these particles clean enough to actually do these kinetic measurements. So I appreciate your concern, but it's hard to give a general answer to that.
No, I mean, I get. I think I got your reply. So it's not really of much concern. So you don't have to worry too much about the impurities. You can work in regular electrolytes without substantial purification.
I don't want to say we don't worry about impurities. We use highly purified water and purified electrolytes because there's just like you do with conventional.
Right, but not beyond that. Yeah.
Go ahead.
No, it's okay. Go ahead, because I just wanted to go with another question and we could proceed. So, okay, so maybe last question that Maria Kelly is asking about the resources discussing nanoelectrode restructuring and contamination. So I guess it's about the work, how we should work with nanoelectrodes. I think this is a good question because they have some measurements that they do, and they always are struggling with using nanoplatinum electrodes consistently. So maybe there's something that you could provide for general audience too. It's quite helpful.
So we talk about this almost every day in my lab. Platinum nanoelectrodes. Is your electrode stable? Has it recessed? Have you dissolved? You can dissolve under in peroxide solutions or by going to too high of a potential, you can dissolve platinum, and sometimes it'll recess so you don't have a flat disk, and that's an issue. So there's actually an experiment I'm going to talk about, the nucleation experiment. The student doing this, Nick Beatty, measures the current response for ferrocene oxidation before, during, and after these measurements to make sure there's no change in the structure of the electrode. But frequently, and for reasons I can't explain, I don't have a really good answer for. Frequently, when you're working with such small electrodes, all of a sudden there is a big change in the behavior in the current. So some restructuring of the electrode, 10 nanometer size electrode has occurred. It's not terribly surprising. In my lab, we have a lot more confidence in making electrodes that have a radius greater than 100 nanometers than we do making electrodes below 100 nanometers. The reproducibility and stability is much greater when you get above about 100 nanometers.
Okay. Well, I hope that answered the question. I think it's important to know this insight. So thank you. We can proceed, I guess.
Okay. Well, I appreciate everybody hanging in here on this. So I got 3 short stories. The first one is on carrier transport or ionophoretic transport of ions through a lipid bilayer. This is work done by Alex Schmelzer, who's a graduate student, and we're using valinomycin as the model compound. So here's a bilayer that we have. I'll show you the support system, which is important to do these single molecule measurements. And you have valinomycin, and the bilayer is depicted by this red circle. And if you apply a voltage across the bilayer, the valinomycin can bind to a potassium ion at this top interface, transport it through the bilayer, and release it at the opposite interface, and then diffuse back to the top one and pick up another ion. And this is well known. There's lots of different types of ionophores. Some of them are of very interesting for the therapeutic applications. We picked valinomycin because we had some kinetic data on valinomycin that we used to try to predict what we should see. The question is, how fast does this cycle occur? How many times does the valinomycin cycle from the top to the bottom, transporting an ion? And that's equivalent to saying how much current is associated with one molecule of valinomycin. Okay. So the reason we're working with this is because back in the 70s, there was a group, I believe from Germany, the lead PI was someone named Stark, who did a lot of kinetic measurements on transport of potassium by valinomycin and a lipid bilayer, applying 100 millivolts across the surface. These were measurements done with macroscopic bilayers. And by macroscopic, I mean something that has a radius, a circular area of a bilayer with a radius of 50 microns or 100 microns. And they did a lot of classical experiments, pulse measurements, and different types of measurements to work out the rate constants for these 4 steps here. So the first step over here is the valinomycin picks up the potassium. There's a rate constant for that. It's transported across the interface. There's a rate constant for that. It's released and then transported back. And the slow step is valinomycin without the potassium diffusing back to the left side. And if you take the rate data published back in the 50 years ago, you can compute that the current per valinomycin should be about 1.6 femtodiones. And that corresponds to 10,000 electrons per second, all right? And so we thought this is a doable experiment because this rate, okay, if we're doing a measurement in a 1 second time period, this rate is greater than what we predict is the minimum number or the minimum current that you need to measure. But it's really close. This is like state of the art in the literature, and it's just above the theoretical shot noise limits. So this was a sort of a test case. Can you do this? So we use a structure. This is a glass structure up here at the right. There's a membrane with a little nanopore in it, and we paint a bilayer across the surface. I don't want to get into the details of this, but you have an aqueous solution up here, an aqueous solution up here, and the bilayer is deposited from a solution containing lipid dissolved in decane. So there's a little torus region around the circumference of the nanopore that contains decane, and it contains excess lipid as well. And the confinement part of this is that the orifice of this nanopore is so small that you would expect when you put the valinomycin in the bilayer, you're only going to get a few molecules in the active region where the potassium is being transported, all right? And so I've drawn it here with 5 or 6 molecules. I think typically we see 20 to 100 molecules in the bilayer above the opening here. But what we're doing here by making this nanopore really small, we're reducing the number of molecules that we're going to make the measurements on. And so instead of having 10,000 or 1 million valinomycins in the bilayer, which is typical of these classical measurements, we just have a few, and that puts you in the ballpark for making single molecule type measurements. And so the experiment is simply to use two silver chloride electrodes and apply a potential, and then measure the current that flows across the bilayer. All right, so here's a typical example. You put the bilayer, now this is picoamps scale. All right, so this number right here corresponds to 60 femtoamps, and the absolute value has no meaning here. This is the bilayer current. This is the current when you just had the bilayer before you put the valinomycin in the solution. All right, so that's our 0 point baseline current. And then you inject the valinomycin into the cell, and you see an increase in the current, and it levels off. It's about 40 femtoamps. And so based on this value that we extracted from the kinetic data of 1.6 picoamps, this should be femtoamps, 1.6 femtoamps per molecule, we can estimate there's about 25 valinomycins in the bilayer. The other thing you'll see about this, if you kind of look closely, the noise over here before you put the valinomycin in is smaller than it is over here. You see a lot more structure after the valinomycin is in the molecule, a lot more structure in the current time trace, okay? And we believe that structure is actually is a measure of the fluctuation in the number of valinomycins in the bilayer film. So here's a blow up. That's, you know, this measurement over here, 30,000 seconds, this is an 8-hour trace. All right, really long measurement. This is 40 seconds of the baseline current, 400 seconds, and this is 400 seconds of the limiting current when the valinomycin is in the film. And you see there's more structure. It's noisy, but there's more structure when in this current time response when you have the carrier molecule in the bilayer. And what Alex has done, she's developed a Python script that lets her go in and it's completely automated and determine where statistically there are steps in the current time trace. So that's what this red line is here. And it's also shown up here applied to the baseline data as well. And so, you know, when you draw the red line in, now you can imagine there's steps, but there's so much noise here. It's not just looking at one of these steps, it's not overly convincing that this is a molecule, valinomycin, when the current increases. This is an increase in valinomycin in the bilayer from, say, 25 molecules to 26 molecules. We think this step structure represents the valinomycin moving from this torus region where you have decane, and it's very soluble in the decane, up into the bilayer film. So the valinomycin, the model is the valinomycin's moving from the active region into this torus region and back and forth, and there's a steady state or an equilibrium partitioning between the bilayer and the decane phase. But anyway, if you take the data and you look at the distribution of these steps, this is what it looks like. This is for the baseline trace. This is what it is when you have the valinomycin in the film. Both of these distributions represent nearly 8 hours worth of data. All right, and it's a one-to-one comparison using the same analysis techniques, the same solution, the same bilayer, same experiment. And what you see up here in the bilayer baseline, there's essentially no steps that are being measured or detected by the Python script. And down here, you get this bimodal distribution that's centered at 0 current. And it's symmetrical, and it's got a peak at plus 1.34 femtoamps and a peak at minus 1.33 femtoamps. There's two peaks here because this one represents the number of valinomycins in the bilayer increasing by 1. And this one represents the number of valinomycins in the film decreasing by 1. And so the step change that we're looking at here, there's noise in it. We don't really understand all the noise in this measurement, but it's plus or minus 1.3 femtoamps. And from that kinetic data back in the 70s, the prediction was 1.6 femtoamps. So we think we've got this experiment working really well. The Linomycin is not very interesting, as it doesn't have any biological use as far as we know, but there's lots of ionophores that do have therapeutic applications. And so now that we got this method, this is an example of developing a method where you know the answer, but you show you can do it. You can make the measurement at a single molecule level. So we're really happy. This is really an exciting result in our lab that we're getting ready to publish. Okay, here's the second short story. Single electron transfer at an electrode electrolyte interface. All right, this one's tricky. So I pointed out, I said before, you can't measure a current associated with a single electron transfer. All right, what you'd like to do, all right, is the ultimate measurement, I think, in single particle counting is you have one molecule, in this case, ruthenium hexamine, and it gets reduced at an electrode surface to the 2+. This is a fast outer sphere reaction. There's one electron transferred. Can you measure that? For one molecule, one electron for one molecule. This is work being done by Jordan Janis. She's a graduate student, along with a postdoc, Dr. Amir Hassini, in my lab. So if you look at this, this is not, you can't measure this. You just can't measure it. But you can think about strategies for doing a measurement. Oh, here's the equation. You need an amplification in a 1 second measurement. You need an amplification of 2100. All right, that's the minimum theoretically to be able to pull this measurement off. So how do you do this? Well, we have a really crazy way of doing it. It's not useful. This is sort of more of an intellectual curiosity. Can this measurement be made by some type of process? And we're using chemical amplification to make this work. And so if you reduce ruthenium hexamine to the 2+, you can use that to electrocatalytically reduce another molecule. And the molecule here is peroxydisulfate. So the reduction of this guy is really slow at the electrode. It's immeasurably slow at the potentials we're working at. But the 2+ can reduce this molecule very quickly, and you make sulfate, and you make the sulfate radical anion, and the sulfate radical anion goes back to the electrode where it picks up another electron to make sulfate. So all we've done here, we put one electron in, and then we get another electron out. So we get current doubling reaction here. But that doesn't do it, because you can't measure 2 electrons either. You need 2100 or a very large, much larger number. All right. But here, if you add another species to the solution, this is oxalate, okay? What you can do is you can take this persulfate radical, and instead of it going back to the electrode, it can be used to oxidize oxalate to CO2 and CO2 radical anion. And so what happens is now the electron going into the persulfate is not coming from the electrode, it's coming from the oxalate ion. Now you got CO2 radical anion. This guy is super strong reductant, and it can reduce persulfate very rapidly, probably close to diffusion control rates. And now you generate another molecule of, another ion of this sulfate radical anion, same as over here, and it can now oxidize another molecule of oxalate. And so this goes on and on. All you need, you put one electron in, and then this reaction takes off. Theoretically, you only put one on, okay? All right, so you get a huge amplification. This is how we depict it, because this is another way of showing this chemistry. And we call this the persulfate oxalate ping-pong reaction. You put an electron in, this is the player serving, this is the ruthenium hexamine, puts one electron in to reduce persulfate. It actually goes through this this unstable radical anion that very rapidly decomposes to sulfate and to the radical anion. The radical anion crosses the net. It oxidizes oxalate, which generates the CO2 and CO2 radical anion. And this guy comes back over here, and it just keeps going. It's a self. I'm not sure. I can't think of the word right now. Self-sustaining reaction. All you need is one electron here to get this going. And if you're working with molar, concentrations that approach molar, millimolar or molar levels of sulfate or peroxydisulfate and the oxalate, you put one electron in and this guy keeps going. Theoretically, you end up oxidizing every molecule of oxalate and reducing every molecule of persulfate. And the amplification you get is on the order of Avogadro's number. All right. Everything in the beaker is oxidized and reduced by injecting one electron. And the way you can detect this, theoretically, you can put an electron in over here, and then you measure the amount of CO2 that's being generated. All right. So let me show you some preliminary work on this. We're getting pretty close to getting this to work. So here's the first step, the reduction of ruthenium hexamine. This is the black CV, perfectly reversible curve. And then you put in the persulfate, and you get this irreversible red curve. So you're adding persulfate here. And it's irreversible now because it's a catalytic, it's an EC prime type reaction. It's a little bit more complicated because you get the second electron here. But the increase in the current from the black to the red represents the catalytic reduction of the persulfate, and then you're recycling the ruthenium close to the surface. And then you add oxalate. Oops. You add oxalate, and what happens is the current goes down. And the reason it goes down is because this persulfate is not making it back to the surface, but it's being used to oxidize oxalate. And that's a chemical reaction. You can't detect that at the electrode. That's invisible to the electrode or the electrochemical signal. Okay. And you keep adding more oxalate. And you get this reaction to go. What happens is you start, I got too many curves here. You start with the reversible response for ruthenium hexamine. You add the persulfate, the current gets really large. And then you keep adding more and more oxalate, and the current decreases, and it goes right back to the original ruthenium hexamine reduction CV. All right, the curve when you just have ruthenium, and the curve when you got oxalate and persulfate and a lot of oxalate, those two curves are very, very similar to each other. It looks reversible. All right, and what's happening here is once I get this thing started, all right, all of the oxalate, all of the persulfate now is being reduced through this chain reaction right here. All this chemistry going on, which could be millions or trillions of electron transfers in the solution, is completely transparent to the electrode. There's no current here associated with the homogeneous chemistry. And all you end up seeing is the reduction of ruthenium hexamine. This is a plot of the peak current versus the concentration of oxalate. And so this is when you have persulfate in the solution. That's the electrocatalytic current. And then you start adding oxalate, and that current goes back to the peak current for the reversible reduction of ruthenium hexamine. All right. So that's one bit of evidence that this is all working. We also do bulk electrolysis because this is more convincing. And so what we're doing is preparing here a solution of ruthenium hexamine and peroxydisulfate. And we apply a potential where the ruthenium hexamine is reduced and then this persulfate is catalytically reduced. And you measure the electrolysis curve, current versus time. The area under that curve, this red shaded area, corresponds, using Faraday's law, to the number of moles of ruthenium hexamine and persulfate that you added to the solution, just as it should. This is a really simple experiment. And then you take the same solution and you add oxalate. And what happens is you measure a charge, but it only corresponds to the number of moles of ruthenium in the solution. You're no longer getting charge resulting from persulfate reduction at the electrode. It's all happening homogeneously in the solution. Okay, so how do we know this is happening? We take CO2, Jordan takes CO2 and bubbles it through a solution with barium chloride, high pH, to make barium carbonate, which is a solid, and you can isolate this. So an electrolysis experiment like this, she's making macroscopic quantities of CO2, putting in very little current and getting out a huge amount of the product here, all right? Okay, so within error, we measure this charge. We can't measure any extra charge within error due to the reduction of persulfate. Okay, and so we actually can't actually measure how many electrons are needed to set off this chain reaction here. It's immeasurably small, both from the CD experiment and the electrolysis experiment. But we're getting out 10 to the 21 molecules of CO2 out the back end of the reaction. And so theoretically, the amplification should be 10 to the 23rd. Of course it's not, because you're going to lose some of these radicals by side reactions. But it must be really large, the amplification here, because we're getting out macroscopic quantities of CO2, and we can't measure this. The charge needed to carry that out is so small that we're unable to measure it at the current time. So the amplification must be really, really large. We don't know what it is. I can't tell you what it is. I can't tell you if it's greater than this 2100 that you need. It's certainly not this number. We're hoping it's really somewhere in between, an amplification, I think, of 10 or 20,000. If the ping pong ball goes back and forth 10 to 20,000 times, then we should be able to actually inject a single electron and see it by analysis of the CO2. Now, we're not going to do this. I haven't told you how. We really haven't developed the correct technique for measuring CO2. We don't want to isolate solids in this experiment. We're going to use electrodes that are sensitive for CO2, put them very close to the electrode where you're injecting an electron, and see if we can quantify what this amplification reaction really is. Okay, do I have time, Andrew, for one more 10-minute short story?
Yes, absolutely. Feel free to use as much time as you want. Yeah.
Well, I don't want to use everybody else's time. So this is work that Nick Vitti and Pavel Majumdar are doing in my lab. They're both looking at nucleation phenomena. Pavel's really working on nucleation of gas phase, looking at nucleation of bubbles. Nick's working on nucleation of metal particles. They've been working together a little bit on this particular project. And the experiment, this voltammogram here, is looking at the deposition of a silver particle on a platinum microelectrode, a small electrode. Okay, and so the CV, this is very classical. You scan, let's see, here's the scan, you're scanning negative, and there's a little sloping background curve here that's not important. But you get out here to this point, you nucleate a silver particle, so there's a nucleus formed, and the particle starts growing. You get a limiting current because you're limited by silver ion being transported to the particle where it's deposited, and then you can come back and strip it off. Okay, and so that's been in the literature for 80 years, I suspect. This is a really old experiment that a lot of you probably have done. And if you do this with a tiny electrode, so this is a platinum nanodisk with a radius of 156 nanometers. Oops. you get the same response. In fact, you really can't tell the difference between these unless you look at the current scale. All right, you scan out, you nucleate a particle right here, and you grow it by diffusion limited growth, and you can strip the particle off, and this is reproducible. All right, the difference in the areas of these two electrodes is it's a factor of 10,000. This electrode is 10,000 times smaller than this electrode. When you do the experiment on this electrode, you get many nuclei, many particles on the surface. And when you did the experiment with this tiny platinum nanoelectrode, you only get one particle, one nucleus, one particle. And this is, I'll show you how we figured this out. So the classical way people study nucleation, kinetics of nucleation, is by potential step experiments. And so you step the potential where there's no metal deposition out to a value where a negative potential where you're reducing the silver ion, and you record a current that looks like this, something like this. This is double layer charging. This is this is the charging current decreasing, and then somewhere in this range here, you're starting to nucleate particles. They're starting to grow, so the current goes back up. This is a well-known response function. And you can step to different potentials, and the curves change because as you go to more and more negative potentials, the over potential or the driving force for nucleation is increasing. And so this is the response here is a function of where you step, okay? And if you do the experiment twice, you get essentially the same curve. And if you do it 100 times, you get essentially the same curve each time, all right? And this is, you can model this. There's differential equations or expressions that take into account the kinetics of nucleation and the diffusion of the silver ions. And the equations are just horrendous, but there are equations that will allow you to model this response function, all right? And they're all deterministic type equations. All right, you do this at the nanoelectrode, same potential step. You see, here's the double layer charging, decreasing, and then there's no current, and then boom, you nucleate one particle. That's a stochastic process. And it's stochastic because if you do the experiment over and over, these are 5 traces for the same electrode, the nucleation event occurs at different times. The beautiful part about this is you can immediately see, you can measure where nucleation occurs when you only have one particle and you're using a small electrode. And you're using a big electrode, you can't tell where the nucleation is occurring. You can model it mathematically, but you can't measure the actual, where the times, the points in time where the different nuclei are forming, okay? Sometimes you get a nucleation event and you get another nucleation event on these small electrodes, all right? This is very infrequent, all right? Most of the time you just see one event here. I don't know why, I don't mean to have 2 red, that was a PowerPoint. There should just be 1 red star here, not 2, because there's only 1 nucleation event. But here there's 2 nucleation events. And the number of nucleation events that you, when you do this experiment over and over, it follows a Poisson type distribution, where for this size electrode, the most common outcome is you get 1 nuclei to form in about 10 seconds, sometimes 2, rarely 3, and sometimes you don't get any nucleation for tens of seconds, all right? It's all stochastic. All right, the nice thing about this experiment is we can measure the time to nucleation. We can do this over and over, get thousands or hundreds of event times, nucleation times, and then using a Poisson type of analysis, we can calculate the characteristic frequency of nucleation. What we're interested in here is understanding when you change the overpotential. If I go from right to left here, I'm increasing the driving force for nucleating a particle. And this corresponds to this free energy curve over here. This is free energy versus the size of the particle. And these curves are for different overpotentials. And so this blue curve right here, or teal colored curve, is at a low overpotential. And the blue one down here, the red one here, is at a high overpotential. And nucleation theory is a very classical model here. It says there's an activation barrier, right? There's an activation energy associated with nucleating a new phase. And that activation energy, or this maximum in the free energy curve, as the particle's growing, occurs because there's two contributions. There's a positive surface energy. You're creating a new surface. That always costs you energy. But you're also creating a bulk material, and that's a negative contribution. And so when you sum those up, you get a maximum in this free energy curve. All right? Okay, the maximum occurs at the critical and stable size of the nucleus. Okay, what I mean here is, and let's look at the red curve right here. You can nucleate a particle, say this, and it can be growing, and you got to get to this maximum. And once you reach the maximum, then it's all downhill. The particle is stable. So you got to grow the particle to this critical size before it's stable. If I'm scanning out along this curve here, and I'm up on this curve, the blue curve at low overpotentials, well, I'm creating particles all along this curve here, but they're not stable, so they just dissolve. So as I'm moving along here, I'm actually getting particles forming, but they're unstable and they dissolve. All right. The question is, what's the critical size of the nucleus as a function of the electrode potential? All right. And that's what I'm going to tell you about here. So we take these current time traces where we can very precisely measure the nucleation time. This one's at about 4 seconds. And you do that over and over. And you use a Poisson, you describe the times by a Poisson type process. You can compute a characteristic rate of nucleation. That's what's being plotted here. And then we're plotting this as 1 over the overpotential squared. And that comes from critical nucleation or classical nucleation theory. All right, I'm not going to show the equation. But the theory says if you plot log of the rate of nucleation versus this inverse of the square of the overpotential, you should get a straight line. And indeed, we do. It's a straight line, and the error bars are small because we measure lots of events up here. All right. Okay. So what do you do with that? Well, without getting into the theory or all the math on this, there's a very simple expression that you can derive, all right, where you can compute the number of atoms in that critical radius, n is the number of atoms, from the slope of this line. And the equation has KT in it. We know what those numbers. It's got the charge of the ion silver +1. This is the charge of an electron. And it's got the overpotential raised to the 3rd power. And so you don't like parameters raised to the 3rd power in experiments because that always introduces a lot of error. But this overpotential is something, this is just the electrode potential. We can measure that within a millivolt or much better. So there's really very little error here. And of course, in these constants, there's no error whatsoever here, okay? And so here's the set of results. These are the overpotentials that we're making the measurements at, all right, corresponding to these 5 points here. And then you can, using this equation, you calculate the number of silver atoms in the stable nucleus, the critical size nucleus. And you see at low overpotential, we're getting 6.1. And as you got a higher potential, this number decreases and decreases. Of course, this has got to be a discrete number. So we assign, I mean, we could be wrong, but we think this 6.1 really corresponds to 6 atoms. And of course, the 3.9 to 4, et cetera, et cetera. So we're calculating the size of the nucleus, but it's in terms of the number of atoms. And there's no assumptions in this measurement about the surface tension between the silver and the solution or the geometry. of the nucleus. All right, this is an equation that just gives you absolute numbers of atoms as a function of your overpotential. And so now you go back to the basic science. The question was, you know, is when I'm doing these nucleation measurements, I do a step potential. I step to here, and that's a low overpotential, 60 millivolts. All right, here that corresponds to the critical nucleus being 66 atoms. That's this going down from here, just going down to the x-axis. Well, I guess it's labeled right here, six atoms. So we know what the intercept here. We know where the maximum in the free energy curve occurs. And you can do this atom by atom. So this is what it looks like. You go to larger overpotentials, the activation barrier gets smaller, the critical size radius gets smaller. You get out to 1 atom. When you're at 1 atom, this is right at the limit of what we can measure because nucleation is so fast. So once you get to this potential range, this is the range where people consider the nucleation to be instantaneous nucleation because it comes so fast. All right, and all you can see, you can't see the nucleation kinetics. All you can see under those conditions is the growth of the particle limited by diffusion. Okay, anyway, this is a really cool experiment. I never thought, you know, I showed you those STM images and I showed you the single molecule images. And when I was in graduate school, 1978, it was totally inconceivable that you could see atoms and molecules. And all these single particle experiments, single event experiments, where we're counting atoms and we're measuring the current associated with one molecule, that was really inconceivable. People really just didn't think about that very much before 1995. Anyways, those are 3 examples. Here's a summary. Nanoelectrochemistry, these are not niche topics. They're really important in energy research, biochemistry, materials medicine, synthesis. I haven't been used so much in synthesis. We're doing some work with that at the moment, but this stuff, this is really becoming mainstream in electrochemistry. You see as many current time traces for a single particle experiment as you do CVs for molecules dissolved in solution, all right? Lots of opportunities. You know, every time you come up with a research project, you can think about doing it the conventional way, or you can think about doing it on a particle by particle or molecule by molecule basis. And you got to think about which way is the best way. Which way do you get the most information, or do you get different information by doing it conventional measurements versus single particle measurements? Method development. Again, I think there's been some criticism of this in the community. It's underappreciated. But boy, you have to have this for future research. If you're going to do really fundamental studies like this nucleation, you know, I just talked about the nucleation of these silver particles. Well, you know, it took us, I don't know, 20 years to perfect making platinum nanoelectrodes to make that experiment work. All right, so method development is really critical. And then the other message I gave you is that for all these measurements, single particle, single event measurements, you need both confinement and amplification. And then the last thing is this equation that we've developed for the detection limit or limit of quantification. I look at that as a design tool. And once you have it and you draw it up, then when you think about making these measurements, you got to think about that you need to be above this brown dashed line, above it or to the left. If what you're hoping to do is down in this quadrant of this plot, it's just not going to work. Okay, you're not going to be able to measure what you want to measure. All right, acknowledgements. I really am embarrassed because I didn't list all students and postdocs, current and former, who contributed to this work. They're all it's just been a brilliant group. A great party over the last quarter of a century. I didn't make a list because I was afraid I'd leave somebody off. I knew I would, And then I've been very fortunate to have good funding for this research and other types of research in my lab. ONR, I highlighted ONR, Office Enabled Research, because they've really, for a long time, they've supported fundamental electrochemical research in my lab, and I'm very appreciative of that. Okay, I'm going to stop now. I apologize for going so long. But I'll be happy to hang around and answer questions.
Thank you so much, Henry. It's been an amazing talk, and I think we've learned a lot. So I think we're open to questions. Please feel free to ask questions in person, especially if you have technical questions, because those are much easier to explain if you can do it yourself. So one question was about, okay, go ahead.
Well, I was trying to read some of these questions in the chat.
So one question is there any time delay between the moment that the silver nucleates and when the signal is observed on the IT curve?
What was the question again, Andrew? I'm sorry.
Actually, I can see Hong Ren. So go ahead, please.
Oh, Hong, go ahead.
Hi, Henry. Great talk. I'm very impressed with the results. I'm just wondering, like, actually, two questions. One is there any delay, you think, in the IT curve in those silver nucleation experiments when you start to be able to see the current from like silver deposition? Like, does it like happen instantaneously, or you think there's some delay, like after nucleation, and then it still grow, but you just cannot see it from the current?
Wait a minute. I'm not sure. I got to put this back up because I'm not sure I understand your question. Let's look. Well, this one right here. So we're applying a potential at 0. Can you hear me?
Yes, I can hear you. Yes.
Okay, and then the current, you get this big pulse of current that's charging up the. It's charging up. So it's not really the double air charging. It's charging up all the wires and everything else. Yep. That goes into this, and then the current decays to 0, roughly 0. The offset here, these currents are so small, the offset doesn't really mean anything. And then at this point, we see a sudden break and a sudden change in the current, and we believe that's the nucleation. Now, so what is what was your question? I don't quite.
I guess like if you think about like if nucleation, like from your result, it suggests that there's just a few atoms, 1 or 2, right? And then like when they grow into like, for example, 1,000 like silver like atom like clusters.
So here they're growing.
Yeah, like do you know like what's the size that like I'm just saying that like the moment of that inflection point is like how much current like in terms of detection limit is there, and then like do you need to extrapolate back into when is really your nucleation time?
No, because it grows so fast. Okay, that there's no huge. The amplification, of course, is the growth, right? The confinement in this experiment is using a tiny electrode, so you only get 1 nucleus. And then the amplification, see that signal is the very rapid growth. So you're talking about silver ion diffusion on a 100 nanometer scale. That's just like infinitely fast. Okay, so this is growing really fast. And once you're out of the noise, see where my pointer is? Mm-hmm. If I say I'm out of the noise here, or it's disappeared. At that point, the particle has grown from 1 or 2 atoms up to about 1 nanometer in size, thousands of atoms. It's really fast. I mean, look at the time scale. This is seconds. Mm-hmm. So electrodeposition on 100 nanometer scale is just incredibly fast.
Got it. All right.
And this actually is kind of a nice way to grow a particle. I mean, if I wanted to do studies of 1 particle, I'm not sure why I'd want to do this, but I could nucleate this and then tell the computer to automatically shut off the potential when the current gets to this point or this point or this point, and then you can grow particles of a predetermined size.
Yep. Very beautiful work. Thanks.
Thanks, Hong.
Please go ahead.
Go ahead.
There's another question that I see.
Hi, thank you for the very interesting talk. And I thought the ping-pong amplification was very interesting. And I have more of a suggestion rather than a question. And
Great.
I believe the issue was that you're reducing the Ru hex, and then you're almost quenching the persulfate by reducing the persulfate at the platinum at the same potential. So I just thought, if you have your platinum electrode and you have an anionic SAM, you'll be able to maintain that perfect outer sphere reduction of your Ru hex, your cationic species, but due to electrostatic repulsion and the fact that the persulfate is an inner sphere, you should be able to switch that off completely. You might replace the persulfate to Ru hex.
Yeah, I understand it. That's a really great suggestion. It turns out we simulate all those voltammetric responses. We put the mechanism and simulate it. And once you if you just have the persulfate and you catalytically reduce it, all the SO4 radical makes it back to the electrode, all 100%. If you put the oxalate in high concentration and you look at the simulated concentration profiles, about 1 in 1 million of those radical anions actually makes it back to the surface, because the oxalate is a much better scavenger of these, because it's homogeneously distributed, of the persulfate radical than the electrode is. But your suggestion is actually well taken. That's a good idea. I don't think we need it, but it's good.
Maybe next time.
Yeah, thank you.
Thank you. Go ahead. Next question.
Okay. Hi, Henry.
Hi.
A question for your last story, the silver UPD on platinum. So I noticed the critical nucleoside is on the angstrom level. Is that more like because of the defects of polycrystalline platinum as nucleation size? Then when you have like a single crystal platinum, I'm thinking like the nucleation would be almost like instantaneously you grow as a monolayer. There won't be a critical size, right?
Yeah. No, you're really, that's a great question. Of course, we can't make single crystal nanoelectrodes.
Yeah.
Okay, so let's forget about that. All right, that would be really nice to do that. I think you're asking, do surface defects affect nucleation?
Yeah, at least you can control the defect level.
Yes, absolutely. Yes, every electrode we make, there's a different potential dependence. All right, where you get 4 atoms is different on one electrode than it is on another electrode. The activation energy, on some electrodes, the activation energy is low, some electrodes it's high. And we study this in great detail with nucleating single bubbles and nanoelectrodes. And there, the activation energies can vary by a factor of 3 from one electrode to another. And that's got to be associated with the surface structure of the electrode. The surface structure on each electrode is slightly different.
I see. So
we can't get around that. But that's kind of a nice thing too to see, because that's what you would expect. I mean, this is all heterogeneous nucleation, so it should depend on the surface structure.
I see.
Right?
So the silver UPD, the potential actually would be already bulk deposition, right? You scan the potential.
Yeah, there's an overpotential. So the overpotential is measured from the bulk deposition potential.
I see.
And so to nucleate a new phase, you always have to apply, to get it started, you have to go an overpotential relative to the bulk, the thermodynamic value for the reduction of the metal ion. This is true for all nucleation processes. There's always an overpotential or an activation barrier you have to overcome, because you're creating a new surface. And certainly that costs you, that's positive energy. Okay.
Okay. Thanks.
Yep.
Thank you. Anyone else? Okay, maybe I can ask a few questions and
Sure.
we will see. Okay, I see one raised hand from Tom. Tom, go ahead.
Yeah, hi, Henry. Really great talk.
Hey, Tom.
Yeah, hey, when we were growing...
You're not an electrochemist.
I know, sorry.
Yes, you are.
When we were growing metal nanowires in AAO, you know, very small pore sizes, some metals always came out as single crystals. And that might be just again, because the nucleation is a rare event compared to growth.
Right.
And so by electroplating certain metals, like gold, for example, in the right kind of pore, I think you could make a single crystal facet tip. Can
you measure the orientation? I guess you can.
Yeah. And the orientations are quite consistent, depending on which metal. Some metals are really polycrystalline down to a couple of nanometers, but some are beautiful single crystals, platinum and gold, for example.
Platinum is?
Mm-hmm.
That'd be worthwhile. You want to help us with that?
Well, we could try, sure.
Okay.
We have a plating solution. Yeah.
Okay. I don't want to.
If you have a pore,
I don't want to relearn how to make the wheel.
Yeah. Okay. We can talk.
Okay. Great, Tom. Good seeing you.
Thank you. So I have a couple of questions. So one goes back to what you discussed about the specific events. So whenever you detect the event, my understanding is that you mostly look at the actual fact of the event. Something happened. So say a particle hit the surface and then you see it as a spike, or a molecule, maybe even a biomolecule, touched the surface and then you see a spike. So do I understand it correctly that based on the statistical limitations that you show, that it is very, very unlikely that we will ever be able to resolve that single event? So see the structure of that event. So sort of resolve this, because there might be multiple electrons transferred, or the molecule might be rolling over the surface, and then you would see what's the inner structure sort of the event is. But it looks like
let me show you something real quick. If I can, I know what you're saying. I got it. Okay, share. And let's go back to this beautiful experiment from Richard Compton's lab. I get to it real quickly, sorry. Okay, let's look at this experiment right here. This is a silver, I forgot how big the particle is, 10 nanometers, roughly. Mm-hmm. And it collides with the surface. The electrodes, the potential sets, so it oxidizes the silver. And you see one peak here, it's actually, you oxidize all the silver. Okay, and then if you wait, this is on time scales of, this is, the width here is on the order, what's the width of a few
millisecond or so, yeah.
Something. And if you wait long enough, you'll see another peak, maybe 5 seconds later, right? It depends on the concentration, how these peaks are spread out. I don't have the slide for it, but it turned out a couple of years ago, at the very same time, Bo Zhang's lab redid this experiment, Pat Unwin's lab redid this experiment, and YT Long's in China, his lab redid this experiment. We all showed up at a Faraday discussion, and we were shocked that we'd all repeated this, but we repeated this with a much higher bandpass filter. So we to resolve, to spread out this peak in time and resolve it, what it really looks like. And it's not when the particle comes down, what you see is you see a peak, and then maybe a millisecond later, you see another peak, and then you see another peak, and you see another peak. And what's happening is the particle's hitting the surface, and when it hits, it gets oxidized, but then it diffuses away, and then it hits the surface again. And so you end up typically with about 10 peaks. If you resolve this, a faster time measurement, you'll get about 5 to 10 individual peaks here. And it's corresponding to the diffusion, random walk of the particle at the surface. And that's all been modeled now. And it's actually a very informative, it's a really great experiment. You really learn a lot fundamentally because you can actually, you kind of realize that, well, when a particle or molecule comes to the surface, it doesn't hit the surface once and diffuse away. It's hitting the surface thousands of times, if not millions of times before it diffuses away. And so this single particle experiment where you get big bursts of current each time the particle hits actually lets you resolve the dynamics of all that. And it's been beautiful work. I think YT Long is still doing some work on this.
So yeah, I mean, that's what I mean. So it sounds like this could be a pretty interesting research direction, right? For the future generations, at least those who work in this field.
Absolutely.
There's plenty of room to explore.
This is an incredibly broad field. And there's lots of really great fundamental questions that need method development and need being addressed.
Mm-hmm. Okay, maybe then the last question, that if we could go to your conclusions, I'm curious if you can add anything on top of the short list of things that have been developed.
The conclusion, the summary slide?
Yeah, the very last slide. Yes.
Oops.
The previous, yeah. So you've said that the field has been developed quite substantial, and we can see 20 years, many people have been working this, especially in the bio, now it's becoming very popular. How do you see which directions, maybe a bit more specifically, you see as the most promising ones for the younger generations, the people who might be interested in going into this field and maybe starting their own labs working in this field? Which ones are the most promising ones? Yeah.
You know, I think a lot of the fundamental work on the particle collisions, a lot of that was initially aimed at catalysis. I'm pointing towards energy here. And that really hasn't worked out. The measurements really haven't given a tremendous amount of information that you can't get from other methods. But I think there's, as you said, there's lots of biological stuff. I think in materials and synthesis, there's really very little. I think this is a really great area. I mean, that last experiment I showed, the nucleation, being able to control the number of particles and the size of the particle. And of course, depositing silver is not interesting in the least bit, but depositing alloys and learning how to synthesize those.
Or lithium. Yeah.
Excuse me?
Or lithium.
Or lithium. I'm not real excited about lithium, but yeah, you could deposit lithium too. Thank you. Nucleate, and that's very relevant to battery research. So I think there's lots of opportunities here. It's these techniques can really be broadly applied. I mean, it's not hard. This research we're talking about here is not. These experiments are not difficult. They're not expensive, and it really is just kind of endless of what the applications are. It just takes a little. You just have to think about what problem you're interested in electrochemistry, and should I be doing the experiments using classical methods, or are there opportunities to go down to the nanoscale?
Mm-hmm.
If I had, your question's really good, and I could say some things, but you really need a crystal ball to say anything useful. And I don't have that crystal ball. So I don't know exactly where. I think synthesis, here at Utah, we talk about using clusters of atoms and particles for organic synthesis. Mm-hmm. And there's hardly anything done, but there's lots of opportunities there. Okay. Mm-hmm. So I think it's just a matter of using your imagination.
Okay, that's great. Okay, thank you so much, Henry. It's been our pleasure to host you here. And we really hope that you will be interested in attending future talks as well. So, but
Oh, yeah,
at this point,
go ahead.
No, go ahead.
I was going to say, yes, I'm attending them already. I plan to attend as many as I can.
Okay. Okay, thank you so much. So at this point, then, we're ending the colloquium for today. Thank you so much.
Thank you.
Thanks, Henry.